chi-squared goodness of fit hypothesis tests, finding the expected frequency values with discrete probability distributions. Example 1, we have a discrete probability table. So we're looking at this example. And our random sample has given us these observed frequencies. So our first step is to calculate the expected frequencies, and then we can carry out the test in part B. So we have our classes into which our observed frequencies will fall into. The sum of all of our observed frequencies is 90. The p-values were already given. And then we calculate the expected frequencies using this formula. The probability p times the total frequency, which is 90. So the first one, 0.2, that's p, times the total frequency, 90, 18. Okay, the next one, p, which is 0.3, times 90, the total frequency, an expected frequency of 27, and so on. These expected frequencies should always add up to the same as the total for the observed frequencies. So this value and this value should be the same. Our probabilities should all add up to 1. All of the e-values are at least 5. So we have 3 degrees of freedom, 5% significance level. The chi-squared tables give us a critical value of 7.815. Using the O and E values from our table, our test statistic x squared is 0.51, which is less than 7.815. So our conclusion is to accept H0 and our conclusion in context. Now this test value, 0.51, is very small, and the reason is that our O and E values are very close together. They're very similar values. You can tell from here there's 20 and 18, they're similar values, 25, 27. If these are close together, then we get a small test statistic. So we have some good results. If there was a big difference between the O and E values, then the test value would be large, and our test statistic would be out here somewhere. In example 2, we go on to the Poisson distribution. So we start with our table, and in the first row we have our classes. In the second row, the observed frequencies, and the sum of the observed frequencies is 80. We're using a Poisson distribution with a mean of 2. Some of the e-values, the expected frequencies, have already been given, but we need to calculate 4 values here. So to work out the e-value for 2 goals, we need a probability that we can use from the Poisson table, so px equals 2, less than or equal to 2 minus less than or equal to 1. And then the formula to work out the expected value, p times the sum of the frequencies. So the probability 0.2707 times the sum of the frequencies, 80, 21.66, that value will go in here. We could have used the Poisson formula instead of the tables, like this. So for 3 goals scored, the expected frequency, using the formula, so we need a probability first, and using the formula to get the probability, we have px equals 3 is 0.1804 times the total frequency of 80, the expected frequency 14.44 here. And working through the table, the last one, more than or equal to 5, we have an easier method to work out the missing values here. We know the probabilities would add up to 1, so 1 minus the ones that we've got here will give us the p-value, and we know the total frequency is 80, so 80 minus all of these expected values will give us the e-value here, and we can see that this value is less than 5, so we need to combine these two classes together to get a new one called more than or equal to 4. So we're going to add these two probabilities and these two e-values, and we're going to add their observed frequencies as well. So our new table, so we have 4 degrees of freedom. There are 5 classes along here, so 5 minus 1, 4. Our H0 and H1, so we're testing both the Poisson distribution and its parameter, lambda equals 2. We're testing both. Our test statistic using our O and E values, 11.79, and using the chi-squared tables, our critical value, 9.488, and we can see that 11.79 is greater than 9.488, so our conclusion is to reject H0. And in the conclusion we need to mention both the Poisson distribution and its assumed parameter. So it's possible that the value of lambda was inappropriate. We had the wrong value of lambda, but the Poisson distribution was okay. Or it could be that goals scored is not a random process. This is one of the conditions for a Poisson model to be valid. Events must occur randomly. So perhaps the Poisson distribution is not appropriate at all. The next example, we'll look at a binomial distribution. So we have our classes in the table here with the observed frequencies, the O values. And we're using a binomial distribution with n equals 3 and p equals 0.2. So we're going to test to see if our data fits this binomial model. So H0 and H1. So mention the binomial distribution with its assumed parameters. The total frequency is 75. And using the binomial distribution, we can work out these probabilities. So using this binomial distribution and the tables, so px equals 0 is the very first one in the tables, that's an easy one. Px equals 1, from the tables you can do less than or equal to 1 minus equals 0 for this, to get this probability. And then for equals 2 it's less than or equal to 2 minus less than or equal to 1 from the tables to get this probability. Yeah, an alternative way is to use the binomial formula. And then to get the expected values, we multiply our p-values with the total frequency, 75. So the sum of all of these expected frequencies should also be 75, the same as the sum of all the observed frequencies. The e-values should be at least 5, so we've had to combine categories together because this one here was less than 5. So we have 2 degrees of freedom. Our test statistic, 6.41, is greater than our critical value, 5.991, so we're going to reject H0. And in the conclusion, we need to mention the probability distribution with its assumed parameters. So now we're going to repeat the test, but this time we're going to use a binomial distribution with 6 trials and a probability of 0.2. So we're using 6 this time. Remember that there are packs of 6 bottles, so this looks like a better value than n equals 3 that we were using before. So our test statistic is now in the acceptance region. We have our new H0 and H1s with n equals 6. So the better test is the one where we're using 6 bottles. So B is the better test.